Okay, so this one we can call a sinusoidal wave, like that. This one up to there, we can say this is t, the time period, so frequency is 1 over t, and angular frequency is twice pi f, which is twice pi over t. So if this one, say this is a voltage wave, this is the maximum value, so we can say V is equal to Vm sine omega t. This is how we designate the wave. Now maybe there is another wave that is of the same amplitude but starts here and then goes there, like that. So this one starts a little ago, say theta angle, so we can say this one, which is another one, say V1 Vm, same amplitude, sine omega t plus theta. This one, the red one, leads the black one by angle theta, and we can see that when t is equal to 0, the amplitude of that one is Vm sine theta, because this much it has traveled already. And similarly, if we have another wave which is like maybe here, starts and then goes like that, something like that, and then this one, say this one is phi angle, so this one is V2 Vm, this one is lagging the black one by angle phi, and this one is, if we extend this one, when t is equal to 0, for V, this one was for V1, and this one will be for V2 smaller case, minus Vm sine phi, because this is actually minus sine phi at t is equal to 0, so sine minus phi is minus sine phi, and this is why this is minus Vm sine phi. So yeah, this is just the concept of leading and lagging. Now if we take a capacitance, and let's say the voltage across this capacitance is Vm sine omega t, and we know the current across capacitance is C, differentiation of the voltage with respect to time. So this one differentiated will become CVm cos omega t, or we can write from trigonometry, this one is sine omega t plus pi over 2. Now if I look at the magnitude part of this reactance, xc, just the magnitude side, Vi, we can see that this one is Vm and this is omega c Vm, so this one. Now when we look at the angle part, we can see that the current is leading because current is ahead by pi by 2, so that is happening because of the reactance also is applying an angle, an adding angle. So the reactance basically is 1 over omega c. If I write in polar form, this is minus pi by 2, or in Cartesian form this is becoming minus j omega c, or we can write, since j square is negative 1, we can write we can multiply both numerator and denominator by j and it becomes omega c, like that. And this one shows that with the increasing frequency the capacitor becomes, the reactance decreases, and at DC the reactance is infinite, at a very high frequency the reactance is very low, like that. Similarly for an inductance, if I look the current, if say the current through this inductance is given by this one sine omega t, we know the voltage across inductance is L di dt, differentiation of current with respect to time. So this is again becoming like that, cos omega t. If I differentiate the sign, it's becoming cos, and omega Lim, again from trigonometry we can write pi over 2. And once again, if I look at the magnitude part of the inductance, inductive reactance, we can see the voltage Im here. So omega L, this is the inductive reactance that keeps increasing with the increasing of frequency, and the voltage is now leading, so current is basically lagging. So the reactance, the inductive reactance is like that, J omega L, or in terms of polar coordinate we can say pi over 2. This is the inductive reactance. So yeah, if I have an RLC circuit like that, RLC, so this is R, this is L, this is C, the total impedance of this one is given by R plus J omega L minus J omega C. So this is how the impedance will show.